Can you guys hear me now? Can you hear me? Yes, okay, good. We're gonna go with this. All right, so, oh God, I don't know how the recording is gonna work. So now you can hear me, good? Respond in one way or another, good. There's a yes over there. All right, so last time we talked about spinors as being irreducible representations of rotation groups. So rotation group, we represented them using 3x3 real matrices that were orthogonal, right? So this were SO3, special orthogonal 3x3 real matrices. Hopefully you recall the definition. Then we had a representation of these guys, right? So, and for a spin J particle, J had to be actually either integer or half integer, right? Integer or half integer. The spinners were the half integer one. And the dimensionality of this representation, we said, is 2J plus 1. So it's a 2J plus 1 dimensional complex vector space. That's what a spin J spinner is. Good. And yeah, what else did we talk about? We last time we also talked about, okay, this was one part of the story. Irreducible meant that you could not decompose the matrices. You could not block diagonalize all the matrices, right? So that's what it meant. All right, so that's one thing that we talked about. Then we talked about the YLMs, right? So what are these YLMs? So let me remind you what YLMs are. So imagine you have a okay, sorry. So this is the source spin. Put this aside. Now we're going to talk about the action of rotation, or this on the spatial part of the wave function. So the way to think about it is that if you have a spin half particle, right, the Hilbert space of that is described using a two-dimensional complex vector space in some auxiliary space, tensored by psi of x prime, right? This is the description of a spin half particle. Well, we could have all sorts of more complicated entanglement, but for the moment, just imagine, well, superposition. This is the wave function of the particle in real space, right? This is the position space. And then this is the spin degree of freedom, right? That we're modeling using this complex Hilbert space. So this is also an infinite dimensional Hilbert space we talked, right? So everything we discussed so far up until the last lecture was about the action of rotations on these guys. Then last time around, we started talking about the action of rotation on the spatial part of the wave function. And then we call this the orbital angular momentum. All right, so that's what the story was. Mathematically, it was very, very similar. We had still the same algebra. We had Li and Lj's, right? Satisfying I, oh God, this chalkboard is so bad. Epsilon I, J, K, L, K, right? So previously, in the case of spin, we had J, I, J, 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 K satisfying the same algebra. Here, we have these L satisfying the same algebra. The distinction is that, so the representations are very similar, except that the half are not, right? Because the wave function in real space going around has to be singled out. This is the way we're presenting it in this class, right? There are, oh, I already ran out of chalkboard. Oh, wow. All right. So are there any questions about this part? I'm going to explain a little bit more, review a little bit more what YLMs are. So this is a review of the previous lecture. So, of course, the way we constructed the Hilbert space here was by picking two operators, as usual, L squared and LZ. They commute, so we could simultaneously diagonalize them, right? We used the notation of ket LM. Sometimes I put a semicolon, sometimes I don't. At the moment, it's a little bit arbitrary, but as we go to the additional momentum, I'll be a little bit more systematic with it. So this was an eigenstate um, simultaneous eigenstate of L squared and LZ, right? So LZ was MH bar, LM, good? All right, so that's what the object is. Now, this describes a wave function in real space. So what this describes is something like this, right? I could talk about, if we recall, this is the wave function in real space. And then we said, if you want to write nice expressions for this, it's better to write it in the polar coordinates, right? So instead of, you don't have to, but it simplifies your life. Why the chocolate is so bad now? R theta phi. Okay. Let me write that here. So pick a unit norm vector. It's basically what it captures for you is it tells you about an angle on the sphere, right? A direction on the sphere, right? So here is the three-dimensional sphere. This n hat unit sphere will tell you about, this is the theta, then this is the phi, right? If this is the Greenwich, whatever. Very definition of where the, yeah. All right, so ket LM, this guy. Let me just write this as theta and phi. This is what we call the YLM of theta and phi, right? These are the YLMs. And they appear every time you have, we're going to discuss that today. Every time you have spherical symmetry, these will appear as part of the description of the wave function. Good? Any questions? Yeah. Yeah, like this guy. What's the name of the group? What's the name of the group? Actually, that's a very good question. What's the name of the group? Rotations in three-dimensional space. What's the name of that? SO3. Yeah, that's what the group is.
So you can have infinite dimensions. Because you can write down the matrix operation.
Precisely. That's precisely. Yes. So just to make a comparison, oh, I erased it. When we're talking about the spin, we're talking about representations of SU2, which is a double cover of SO3 that allowed for half integers. When we're talking about the real space rotations, we're talking about SO3 on the nodes, right? So picking minus signs are not allowed, right? So this is still the same representation theory. Right. Good. So these are what YLMs are. Let me see. Do I want to make a comment to make this a little bit more intuitive? Any other questions? Let me say one thing. Going forward, until the end of the discussion of angular momentum, we're going to have a lot of calculations. And I absolutely recommend that you must do the calculations. These are not arbitrary random things that they're walking you through. These are very important calculations. And viewed simply, after a lot of practice, you develop intuition for this, right? So I'll try to provide intuition as we go every time we discuss it. But there's so much I can do in finite amount of time. So one thing that I want to, now going off. So one thing that I want to remind you is we use the method of raising lowering operators, right? To quantize simple harmonic oscillator. We use the raising lowering operators to construct a representation theory of SU2 and similarly for SO3. What is the basic idea? So I'm just going to say it in this case. Let me just remind you what the story was for the case of simple harmonic oscillator. So you have this lowering operator and raising operator, right? The structure of it is going to be very the same, right? Very much the same. So we had J plus and J minus for the case of spin, and L plus and L minus we're going to see in a bit. Well, we saw that last time, right? Lx plus I minus plus minus I Ly, right? So the idea is that you always have a vacuum. The vacuum is the state that's filled by lowering the operator. This is the lowest level possible, right? So here you could have something. So actually, in the case of J, the representations were finite dimensional. You had the lowest and highest. Yeah.
Zero.
Oh, zero. Sorry. Thank you. Zero. Right. So here you have the lowest and highest. So you can have. Well, you have this, which is 0, minus j, m equal minus j. Hopefully you m equal minus. Well, actually, let me write it as j minus j. Right. This is j and this is m. And then you have the highest one, which is j plus jj equals 0. Right? Similarly for L plus and L minus. Good? The way you construct it algebraic, and this is a guide in physics in general, in a lot of different examples, is that you start first with this function. You know the form of A as a differential operator. That will give you an equation you could integrate to find the wave function of this guy. That's what we did for the vacuum 0. We found it to be Gaussian. Then you generate all the other guys by acting with A dagger to some time, right? And normalized properties. That's what we did. Here, you could do the exact same thing. Here, you could do the exact same thing. To illustrate it, here I have two choices, right? J plus and J minus. We're gonna pick J plus, right? For example, or L plus and L minus, right? So we're gonna pick L plus. We wrote it last time as a differential operator, acting on this guy. Use this equation to find LL. Then order by order, by applying L minus, you construct all the other states, bring them down. That's the basic idea. This is really the algebraic way of constructing things, right? Good. So this is a quick review of what we did last time. I did this explicitly last time. Is there anything else I want to say? But let me draw a diagram because let me draw something here. So say this is the M space, right? So it's from minus j plus 1, a bunch of points, right? J minus 1, j. This is all that there is. You pick here. So j plus or L plus, but L plus moves you this way and L minus brings you back, right? You pick the last guy. You act with L plus. That has nowhere to go. It should vanish, right? You solve that equation first. Then you successively apply L minus to get the other. You could start it from here and go there. As we discuss addition of angular momentum, we're going to draw higher dimensional versions of this. We're going to draw 2 dimensions of M1 and M2 and similar things, just in preparation. So have this cartoon picture in mind. All right? Okay, so this is a quick summary of the last lecture. Are there any questions? Yeah.
So it's kind of a big part.
What's the common interval square element C? 0. Yes.
So then, is there, or I guess is it like redundant?
So the idea is this. Let me summarize it again. You start with the largest set of operators that simultaneously commute. You want that simplifies your life. Then you pick their eigenvalues like ket LM and label your vectors this way. Now you need the raising and lowering operators. Of course, they won't commute. So that's the idea. Good. What was the question? Maybe I did not. doesn't matter. It does not matter. Remember that this, what you pick as to be an LZ is just a choice of coordinates. It's convenience. Of course, you want to pick it to be the one that you're picking to label things. You want to pick that to be the guy. Otherwise, you're making your life hard, right? Because diagonal matrices are easy to work with. All right. Any other questions? So now we're going to talk about lecture 25, which is central potential. So this I squeeze this question, this lecture, because last time what we did was we looked at the differential equation that is satisfied by YLM, right? And I told you that this differential equation, we showed that is the up to 1 over r squared is the radial part of the Laplacian. What is Laplacian in physics, in quantum, regular good old non-relativistic quantum mechanics? I'll give you an intuition. What is Laplacian? P squared. Yeah, it's the kinetic part of a free particle. So if it's it's a kinetic part. So if it's a free particle up to 1 over 2m, right? It's the Hamiltonian of a free particle. So every time you hear those words as physicists, you should think of a free particle propagating, right? Good. All right. So then the question came up that like, do you guys want to hear more about spherically the hydrogen atom? And given that some of you probably going to end up in AMO physics, it's probably good to review this. All right. So what are we going to talk about? We're going to talk about spherical symmetry. Right up here, down here. It's still single particle. Here's your potential. Right? Here's your potential. Now, when I say I have spherical symmetry, tell me how to make this spherical symmetry. Just like remove the vector. It only depends on the distance, not the direction, right? So here's a spherical symmetric thing. And r squared is x dot x. Hopefully that's clear. Right. So what is spherical symmetry? You could check this explicitly that L squared as an operator, which you recall is Rx dot P or X dot X cross X is a very cross. L squared and P squared, they commute. And L and X dot X also commute, right? So I can put this as R squared, then that's clear that this is from which it results that Hamiltonian and L and let me just say L squared. Let me just write this. Actually, let me write down another equation. Hamiltonian and L. All right. So here I'm going to say something. We're going to discuss this towards the end of this course, but let me just do a quick discussion. You have heard this a lot in physics, that every time you have some operator commutes with the Hamiltonian, we give that a name in physics. Yeah, but there's a name that we give it in physics. Huh? Yes, but you know another word for it. Charge, right? An operator that commutes with the Hamiltonian, we call it charge. Sometimes write it as Q. So, and then we say there's a symmetry associated with it. That operator is self-adjoint, it's an observable, which means that if it generates a unitary, if it's a generator of a unitary transformation, that unitary transformation leaves your Hamiltonian invariant. Or how do I want to say that? Yeah, okay. So let me just write it this way. So here's or you could say it this way. If this is your charge, your operator that commutes with the Hamiltonian, you see that it does not evolve as a function of time. We call it charge because it's conserved. Sometimes it's conserved charge. It's sort of redundant, right? So how do I calculate this and show that it's equal to L? How do I calculate this? VCH, exactly. So what is that? This tells me that it's ITHL plus I T squared over 2 factorial, the nested commutators. But you see where this is going. I don't even need to write the other term, right? This vanishes by the condition that we had. All the other terms vanish. So this gives you L, right? So the operator is a constant of motion, as was said earlier. It's conserved. What it means for an operator conserved. Good. All right, I'm gonna say something that if you are a condensed matter theorist, but you must learn. Actually, I think this is a must. Give me an example of a conserved operator for a general quantum system. What commutes with H? Sure. What else? No, you're thinking the right. That's the right direction. That's the right direction. What else commutes with H? Any function of H. Right? Any function of H commutes with H. Good. So it's, as a matter of fact, if you take these are energy eigenstates, any projection like this commutes with H. In physics, this is just a high-level comment. The interest is mostly not anything that commutes with H. Those are charges, conserved charges. We're interested in operators that commute with the Hamiltonian, conserved charges that are local. Right? That's something for you to keep in mind. Good. Locality comes in, but that's a little bit advanced for the purpose of this course. All right. Very good. This writing on the chalkboard really slows me down. I have to do it. And that's what it is on the chalkboard. So the fact that the Hamiltonian and L commute tells me that I can label my kets the following way. Good. E is the energy, I'm not going to write it again, is the eigenvalue of Hamiltonian. And Lm are the eigenvalues of Lz and L squared. Related, right? So my wave functions are going to look like this. ELM of R, theta, and phi. Good? In a lot of physical problems of interest, we could use the following separation of variables. Systems with spherical symmetry, we could use this. This is like up to here. Yeah, this is just some separation of variables that you could assume, plug it inside the differential equations and see. Right, but you will see that this is actually super good. So using this this separation of variables, what I'm going to write down is the Hamiltonian for a particle that had, well, the Hamiltonian was p squared over 2m plus v of r, right? So what I'm going to write down is the Schrodinger equation. H acting on this guy gives you E and this guy. And so I'm writing down the time-independent Schrodinger equation. I'm after the stationary states. Good? So here's what the equation looks like. It's going to be minus h bar squared over 2 r squared del r squared r plus L plus 1 h bar squared. At some point you'll get to a point especially if you're an AMO physicist, that every single term you don't even need to look at. You can just write them down because it's not super intuitive. This is perhaps one of the most fundamental equations that we work with. Right? So already, what I've done is that I looked at this Hamiltonian. The Hamiltonian has a radial part, and then there is an angular part. What was the angular part? Last time we talked about this. So 1 over r squared, right? Up to 1 over r squared, the equation that defined YLMs. So by picking YLMs, here, I've actually solved that part of the equations. I only need to write down the radial part of the equation, Schrodinger equation. Is that clear? Of course, v as a function of r sits with the radial part of the equation. That's why YLM solves the rest. Good? All right. So there's something that's a little bit annoying about this differential equation. Can you tell what it is? Well, actually, I'm gonna do a change of variables. This is so little space. All right, I'm gonna do it. Let me talk high level about this first. All right, because I might run out of time and I want you guys to know what the equation is. You're trying to solve this differential equation. What is the range of the variables? What is the range of R? You're looking at to solve a function of R, to find a function of R. So what's the range of R? 0 to infinity. This is R, this is 0, right? These are very explicit things. The only thing that's not explicit is V of R. Good? So you have to know how V of R behaves near 0 and near infinity. Right? Now comes in your physics intuition. What is V of R near infinity? Really, really far away. 0, right? So, or a constant, right? It has to go away. Then what is V of R near 0? Give me an example of a potential that you do know. No, this is drawing. What's that? Coulomb potential. What is V of R in Coulomb potential? 1 over R, exactly. So it will be basically going 1 over R, right? I've put the sign so that it goes down, right? So and then this, I'm just assuming that I've shifted my x-axis, right? So you expect something like this, right? Your potentials could actually be should have a crazier behavior, more singular behavior down, right? That's possibility. That's something that kids might worry about. I'm telling you, I'm gonna tell you right now, but we're gonna discuss this later. What you would like is a property like this. This is definitely satisfied. This tells you how singular the behavior of V of R is. This tells you that the behavior of V of R is not worse than 1 over R, is less bad than 1 over R squared. It's like 1 over R is okay, 1 over R to the power of 1.5 is okay, right? But R2 is already pushing it. We want this. We're going to see why, actually. This, if the potential is more singular than this near R equals 0, there's something fundamentally wrong with those equations. Can anyone actually guess? You have all the ingredients. I don't expect you to be able to guess at this point, but there's something already. The Schrodinger equation tells you that if the potential is very, very singular, you're gonna write. All right, well, we're good. I'm not gonna have enough time. So, all right, very good. Here, there are 3 things we're gonna do. First, for a reason that I'm not explaining yet, but it will hopefully become very clear, is we're going to make a change of variable, which is this. We're going to divide this R function. Well, sorry. We're going to multiply it by. The reason is that here I have down here I have powers of 1 over R squared. Those are known. Right? If I multiply my equation by R, both sides by R, just one factor of R, there is a smarter way of repackaging this. Good? This is the first thing you do. Point number 1. Point number 2, you look at the behavior of your solution near 0, the behavior of your solution near infinity. You come up with an ansatz for R of R based on that behavior, right? Removing the behavior over there, and then the rest you try to solve. Good. So what we're gonna do is first we're gonna do this change of variable. This will shed light on something important. Then we're gonna look at near 0, see how bad the behavior of the solution is. 0. Then we're gonna look at infinity and see how the wave function behaves over there. So for example, you look at 0 and you find that, I don't know, I'm just making, the behavior of the wave function is 1 over R cubed, making things up, right? So in your ansatz, you remove the 1 over R cubed, right? So you just write an ansatz that has the 1 over R cubed removed. You look at this and you see that the wave function behaves exponentially fast. You put in your ansatz something that removes that exponent, that simplifies your life. You don't need to, you remove the divergence pieces, or that's a general lesson in physics. Every time you're trying to solve a differential equation, first look at the behavior of the solution near the boundary points, use that to come up with an intelligent ansatz, and that's what we're doing. Good? All right, so once you do that, let me just reset. This is del R squared plus R. So I just recycled mine. Is that right? Correct. Okay, yeah. All I did was that I just plugged in. I divided, I multiplied both sides by R and repackaged it. This is what the equation is. Yeah.
Squared, and then the deriving of R squared, or is it dr and then Z squared? Like
No, it's wait a second. Am I? Is that?
like, are you deriving R?
I'm taking derivative with respect to R squared, and I'm taking 2 of them. Yeah. Is that sorry? Ooh. All right, I have to double check that sign, but anyway, I think that's correct. Yeah, that is correct. All right. And interesting things that happen here is the following. You see there is a competition. There are these 2 terms, right? What does it tell you? V of R becomes very negative near the center. This term becomes very positive, so they compete. If V of R has this property that I was telling you, something interesting happens. As you plot this function instead of V of R, I don't have another chalk. What it does is it comes back and goes back up. This is the effective potential that the particle feels because of angular momentum. If the angular momentum of the particle is 0, it just feels the potential. If the angular momentum of the particle is not 0, it feels an effective potential that lifts, right? Can you come up with very, very intuitive terms to describe this? Let me take an extra step. When the potential is, when L is 0, it goes like this. what do you expect for the wave function? Like if this was a classical particle, right? Where do you expect to find the particle? We'll just roll down the potential and come here. When this is the classical potential that's lifted, where do you expect to see the particle? Down here. Not in the center, but a little bit away. As you increase L, you're making this bigger and bigger. This minimum is shifting. Can you describe in words what that is? You know this from your intuition. You don't need to know much physics. A particle, yeah. No, this is no. It is related to orbitals, but you don't need to say anything fancy. What is it saying? It's saying that a particle that has angular momentum, it's hard to put it in the center. It's not. It doesn't want to be in the center. Does that sound familiar? As you give something angular momentum, it gets away from the center, right? If you have something with angular momentum from your mechanics, I don't know, you maybe did this experiment, sit on this chair and you're, what experiments, right? So when you give things angular momentum, you don't expect them to find them in the center. Well, classically, you just calculate where this is, how far away from the center they are, right? Quantum mechanically, there's a wave function for it, but still the peak of the wave function is gonna prefer the minimum, right? This is precisely that physics. So this term is that. The wave function prefers being a little bit away. Now your answer is absolutely correct. It is related to orbitals. It is related to orbitals. But the intuition is very simple. All right. Can anyone tell me why? I guess you cannot. One of the reasons that I took this R out is the following. If I write down the normalization of my wave function, right, R, what does it look like? I have to integrate over the sphere, right? And I have R of PL, R of PL, R. The R has to be 1, right? What did I do when I made this change of variables? It becomes 1 has to be integral V of R, U star of EL, R, U of E. Right? That's exactly why. So my problem in this, when I go to this, I make this change of variables. My problem basically looks like a one-dimensional particle. Right? The wave functions are just normalized as you would expect. That's precisely why it introduces R. There are many ways to modify, but this is one of them. All right. Any questions? So now we wrote this equation in terms of this variable. We are solving a one-dimensional system. It's as if it's a one-dimensional system with this potential, and we notice that this is, I'm going to refer to this as V effective. V effective of R is just lifted in the center. The more angular momentum you have, the more is lifted. Right? All right, what remains to be done? We're going to solve the equation near 0. We're going to solve the equation near infinity and remove the singular parts. And then the rest I'll tell you, we'll work out the examples. I don't know how much time we're going to have, but what we will do at. All right, so I'm going to erase this. Any questions? I don't know if I'm yelling when I write this close. Any questions? This has a name. This phenomenon has a name. Angular momentum barrier. Right? The angular momentum introduces a barrier. It just lifts up the potential. Good. So what does my equation, what do the equations look like near 0? If R is very small, what is the behavior of which term is small? Which term can I drop? This term, right? Because you're adding to it 1 over R squared. This term I can drop. You see, the very statement that the effective potential lifts this assumes this behavior. If V of R was more singular, this would not be able to lift. This is very, very physical. If V of R is like, yeah, it's actually something extremely sick about. I will say it in words. I'll not really have time to reproduce it. There's something extremely sick about the potential that has that's more divergent than 1 over R squared. I'm gonna say it in words. We're gonna run out of time. You could calculate what is the if I so this is the system. If I look at the flux, if you recall, when you solve the wave function, the stationary wave function, we calculated about the flux, right? If you calculate the flux coming of the, which is related to, you remember that sort of, the wave function flux near R equals 0, right? You find that for arbitrarily small regions, the flux doesn't match if the potential is really, really better. That is sick. The wave functions are awful. I mean, the wave function is not really sensible. You lose if the potential is worse than this. You lose the Bohr's interpretation. You can't the probabilities won't add up to 1. Something wild happens, right? No. Yeah, I mean in a bad way. Something like something is thinking like question. Right. No, that's
The
what
first time you
yeah.
said it, I was like.
No. Something ill-posed. Yeah, there's something really terrible about this, and they're unphysical. So lesson learned. If somebody wrote a potential for you, that radial potential that was worse than 1 over R squared, you should raise that eyebrow. Right? Yeah. There's no way to solve this. There are no such forces in nature. There's no, yeah. All right. I am oversimplifying, but if the potential is worse than that, you have misidentified your degrees of freedom. The particle you thought you were trying to solve for is not the right degree of freedom. But anyway, as usual, there's an answer at the level of discourse, and then there's fancy. All right, good. So this term drops out, so I can actually try to solve then the H squared. So I only have these two terms. This guy goes away, right? So I end up with, and this term goes away as well, right? Is that clear? All right. I'll leave that. So you're solving this differential equation, E of R squared. Sorry. Thank you. Yeah, I think I made a mistake. Let me write it this way. This is the second derivative spectrum. I'm confused about my change of variables. I'll double check. I apologize. I'm not sure. I don't remember actually. But it's correct this way? Yeah, okay. Now that I think about it, it can't be. Sorry about that. The DDR square. So it's the second regular derivative of R. I apologize. Sometimes we repackage it as R squared, but not in this case. So this is LL plus 1 over R squared, U of PL R as R goes to 0. The solution to these equations are U of EL L plus 1 plus B R minus L. We must discard this term. Is that clear? Why? we have to set b equals 0. There are various ways to see it, but let me see. How did I? One way to see it is that as L, you increase L, right? The wave function is going to be more and more peak. That's unphysical. But much worse is that if you look at this wave function, if you set b not equal to 0, you run into this issue that the wave function is non-normalizable, blah, blah, blah. This is unphysical. We're going to set b equals 0. So in the notes, I have a more detailed discussion, and Sakurai has a more detailed discussion. Good. So this means that R of E L R, as R goes to 0, behaves like R to the power of L. It's not right here. Okay? So the radial part of the wave function behaves like R to the power of L. Good? When L is 0, that's the spherically symmetric case. You have no angular momentum. Your particle has no angular momentum. So the wave function in the middle has a constant value. That's consistent with the fact that the potential is not lifted. Right? When, as you increase L, the wave function is becoming more, doesn't want you to be near the center. Right? Good. The case with L equals 0 has a name. It's called the S wave. Spherical wave. S wave. I don't know whether S stands for a spherical. But there's something really cute here. Let me write it here. This has a very, very profound. Somebody mentioned orbitals, right? So that is exactly the fact that near the center, the wave function behaves like this. It tells you that the probability. So the probability of finding, let's say you have an atom, right? It has some radial. The center of the nucleus of the atom has radius r, and there's an electron that orbits this, right? The probability of finding the wave function, but the nucleus is really in the middle. It's very, very small. So you could assume that r is always 0. The probability of finding the particle, the electron inside the nucleus is r, right, to the power of 2L. Good. But it's a probability. It has to be dimensionless. What scale comes up? Let's give it a name, some scale. We're going to call it A naught. This is called the Bohr radius. You discover the Bohr radius by a simple analysis like this. Probabilities must be dimensionless, right? So when I said that the wave function behaves like R to the power of L, the wave function, yeah, there's some dimensional analysis to be done. I don't know how much time we're going to have, whether I can derive this in absolute gory detail, but all right. So this is the behavior near 0. The wave function behaves like R to the power of L. Good? As a matter of fact, R over A naught to the power of L. Now, near infinity. Next, I'm going to discuss this near infinity. What do I expect near infinity? Oh, what did I erase this? What do I expect near infinity? Let me, L plus 1 over, I should know this by heart, but 2mr squared minus h bar squared m L. What do you expect near infinity? Which terms drop out? This term drops out. This term drops out. So you're solving, and the problem is effectively one-dimensional. You're solving P squared is equal to E, right? What are the solutions to that equation? It's just a wave equation. Plane wave, spherical plane. But think of it as one, it's just plane waves, right? But it can't be plane recall that for this to interpret as a plane wave, you need to have energy larger than energy at infinity. So if this is 0, you should have positive energy. What is the solution when you have energy less than 0? You get an exponential decay. This is what we saw. This extra I gives you exponential decay, right? So by a simple analysis like that, you learn that, I mean, you don't need to say these words, just try to be mathematically oriented and just solve it. And you learn that U of P is L is like E to minus kappa R, or kappa squared. Kappa is minus 2m P over H bar squared. Good? Because your E is negative, you need to put the minus sign here. And that I turns you from oscillations to decay. So the wave function here, infinity, decays exponentially fast, and here it behaves like U to R to parallel, right? Good. So what do you do in this situation when you're really at the time? What you do is this. You first notice that this kappa is sitting next to your R, right? You define a variable rho, which is kappa R. Rho is dimensionless. One general advice I can have for you guys, every time you're trying to solve a differential equation, use dimensionless variables. It will simplify your life. So you define rho, then here is the ansatz you're going to take. Rho to the power of alpha minus e to the power of rho. All right, why did I write this ansatz? As R goes to infinity, this is the behavior I expect. So I expect as R goes to infinity, right, that this will take care of the decay of it. As R goes to 0, this will kick in. So I expect using this reparameterization of my equations, if I write down just plug in this ansatz inside, you know what ansatz is, right? Okay. A guess for the form of the function. Inside the differential equation, it simplifies my equations. Good? Are there any questions? All right, here's what I'm gonna do. Let me write down the equation up here. And then I have prepared 2 examples, but I think I'll only have time to do 1 example. You plug in that ansatz and you find this is a really awful mistake. This is definitely a squared. That would be that. Plus 2 if I make that mistake in front of more people, they'll yell. I'm not anymore. All right, so this is the differential equation I'm trying to solve. Good. Every time we have all I assume is that I have a radially symmetric potential. That's all I assume. For every particle that moves under the arbitrary potential V of R, your differential, your Schrodinger equation boils down to this one-dimensional equation. Right? This is what you do. Good. Of course, your potential is explicitly in here. I can't solve this as is. Depends on the function. So there are 2 examples in the notes. In the book actually there are 3 examples. but let me do. So I was gonna do the isotropic harmonic oscillator. I'm gonna skip that one. I'm gonna talk about the Coulomb potential. So here's the Coulomb. So cool. So I have a nucleus, some size R, charge Z. What is Z? The number of protons in there, right? And then there's an electron away from it, a distance R that feels the potential minus Z squared. Hopefully that's good. You might be familiar with notation where with Coulomb constant or something, right? Get rid of all of this. You eat them in your with definition. Their equations shouldn't have. Actually, wait a second. Is there even? Yeah, I don't think there's. I don't remember my undergrad. There is something, right? But then you eat it in speed of light and epsilon. There's nothing. All right, good. All right, so how do I describe this? Very good. Once again, what we're gonna do, well, we're gonna solve this equation. Good. So, very nice. First thing is to take care of. First thing is to exactly take care of what which is. So here there's an E, right? That's a dimensional full constant. As the energy that for which I'm solving the differential, see, it would be energy of my stationary state. So the solution, the eigenvalue of that. So let me define this thing, rho naught, which is square root 2m over minus E Z squared over h bar. Why did I put minus? Because I'm after bound states. The particle has energy less than 0. Otherwise, if the electron had energy more than the zero potential is defined the way. If the particle had more than 0 potential, it would not even know atom exists. Just freely product, right? That's why I put this. This you could repackage as one does always. 2m c squared over minus e z times alpha. Alpha is e squared over h bar c. It's about 1 over 137. It's called the fine structure constant. Fine structure constant. It's called fine structure constant. It's just a change of variance. Right? I'm not doing anything. Is the idea clear why I'm doing this? I want to write everything in terms of dimensionless quantities. My rho is dimensionless. I want to build up a dimensionless quantity out of my. That's what I'm. This is alpha is a dimensionless. Right? So hopefully it's clear. This is 1 over 137. Z is the number of protons. 2mc squared over minus e. If you know anything about Einstein, you know this is a number. Good. So this rho naught is a number. When I do this change of variables, my differential equation takes the following form. Rho p squared omega over 0 squared L plus 1 minus rho p omega 0 plus rho naught minus 2 L plus 1 rho equal to 0. Very good. Are there any questions? So I have about 6 minutes. The details are in the notes and in the book, but let me describe it to you. First, I'm gonna pause. Yes. Row 0 minus 2 times L plus 1. Why did I miss the row? You're saying?
You only went to one row.
Here?
Yeah.
Supposed to be a
No,
row?
no, like- You have rows.
Here. No.
Yeah.
Oh, this is, oh, sorry. I copied it incorrectly here. Sorry. Yes. Row D squared. Yeah, correct. That's right. I can't get my patterns right. Good. Good. Now, I have a couple of minutes. Any other question? Another question. Let me make space to solve this. So this differential equation has a solution that's well known called the confluent hypergeometric function. If you think we could get a PhD in physics and get away without knowing about this function, you would be wrong. It's all over the place. It's actually one of the simplest ones. So omega of rho, the solution is function, but it's really intuitive. Is the L plus 1 minus rho naught over 2. There's a derivation of this in the book. So it's that simple. It's so simple that you could derive this from yourself. This is called the confluent hypergeometric function. And if that doesn't, just a name, here's a series expansion. Sum over, that copy this expansion. No, I did. I'm pretty sure I did. Maybe I did not. Oh, well, you'll correct me. Let me just, yes. Sum over n of a plus 1 all the way, or c plus 1 all the way to rho the power of n over n factorial. Then here x of c is 2l plus 1 and a is l plus 1 minus rho naught. Is it correct? I think that should be correct. All right. Good. The 2 is where?
It goes. It's 2A.
That doesn't seem right.
Maybe it's. Yeah.
Yeah. All right, good. So this is what the function is. All right. I'm gonna say the physics, right? When you stare at this function, rho is up to a dimensionless radius. What you first notice, this is supposed to be up to a bunch of constants, a bunch of behavior at infinity that are removed. It's supposed to be the radial part of the wave function. What do you notice about this expression? These are just a bunch of numbers, right? What do you notice first about this expression? The sum runs from 0 to infinity. How does this function behave at infinity? It grows wildly, grows exponentially fast. That can't be. That's unphysical. How could it be that this expression doesn't grow exponentially fast? How could it be? Okay, this is where I've not explained, and I'm running out of time. But let me see how to explain this. Can I look at the book to see or that help me achieve what I want to do? Yes, yes, I can actually do that. Good, good. Sorry, yes. I was living sloppy here. I believe this is like a plus n over c plus n. Rho to the power of n over n factorial or 2 n factorial 2n. Yeah, there's no 2 here. Good. And that's all I need. Yeah, here we go. Okay, so this is the expression. How could it be? Is it how can this function stop growing? I'm actually going to pause and thank you guys. My last one. How can I stop this function? If you see, so this is the first term of this is going to look like a times a plus 1 over, there will be terms that look like this, rho over rho, right? The next one is a plus 1 times a plus 2 over c plus 1, c plus 2, rho 2 plus da da da, right? How could it, yeah. No, if one of these terms becomes 0, if one of the terms becomes 0, then the series will terminate. Because all the terms above for larger n will have a 0 in the coefficient and will vanish. Good? All right. So it must be that a plus n is equal to 0 for some integer n. As a result, you find that rho naught has to be 2 times n plus l plus 1. And n has to be, can be 0, 1, 2, da, 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 l 0, 1, da. You got the quantization of energy, quantumness of the spectrum, out of the fact that the consistency of the differential equation. It couldn't grow forever. Physically, it's impossible. Or it's an unphysical solution. It had to terminate. And it could terminate. There are many ways it could terminate, right? They're all labeled by an integer n. These are the eigenvalues, and they will decide for your rho naught, given their angular momentum. Recall what rho naught was. Can someone say what rho naught was? It's the scale associated to your energy. So what it told us is that the fact that this function cannot grow, it told us that we have an infinite set of solutions that are well behaved in infinity. All what there are in one-to-one map to integers n. They all have a particular rho naught and angular momentum that we calculate, and rho naught is energy. They found the spectrum of an electron around an arbitrary nucleus. Let me see if I have a really badly ran out of time. Let me see if I have a lot of comments, physics comments, but let me see if there's something else I can say. All right, we're out of time. We're out of time. I'll do this next time. So let me just review. What did we do? Today what we did was that, except for the beginning where I went on rants about them before, we took a spherically symmetric potential and we wrote down the differential equation, the Schrodinger equation, to find the eigenfunctions, energy eigenfunctions, for the wave function of a particle that feels the spherically symmetric. We saw that there were 3 things we wanted to do. Some of them were a matter of convenience, some of them. One of them was we first redefined the radial part by this factor r and defined the u function. That was in part because we wanted to bring the question down to something that looks one-dimensional. So that if I integrate u star u against r, I get something that's 1. That's coming out that. Then the 2 other things I did was we looked at the function near 0. and near infinity, we found the behavior of it, and we used that behavior. Near infinity was exponentially decaying. Near zero, it had a behavior. It was R to the power of L. We use this behavior to write an ansatz. We solve for them. Physically, two things happened. There was the effective potential. We saw that the result of having angular momentum was lifting the potential. We call that the angular momentum barrier. That's very, very physical. The wave function wants to be away from the center when you have angular momentum. Then the second thing that I forgot, I lost track. Anyway, so we took the potential for an electron, the potential and electron fields going around the nucleus with number of atomic number z, the number of protons z, and then we solve for it. And if you just these solutions that we just wrote down, I'll probably squeeze it in the next lecture. These are the orbitals. These are all the solutions. One last comment. Are there degeneracies? Yes. How do you know there are degeneracies? M doesn't appear. There we go. Good. There's at least a 2L plus 1 degeneracy. Good. Thank you so much.